Hello students, in this video we are going to discuss about a very important concept in organic chemistry, that is resonance effect, which is also called as mesomeric effect. There are a number of molecules whose behavior cannot be explained by a single Lewis structure. As we have already discussed the case of ozone molecule, to explain their behavior, two more or more than two structures may be proposed. So, these structures are called as resonating structures. And the actual molecule is said to be the resonance hybrid of these structures. We already discussed about the resonance concept in the chapter, that is in chemical bonding chapter. So here the ozone molecules which can be represented by two structures, these are called as resonating structures. So the actual molecule, its behavior cannot be explained by these structures, but it can be explained by the hybrid of these two structures, that is called as resonance hybrid. So this phenomenon is called as resonance. That is, if a molecule can be assigned two or more structures, that is shown here. So none of these is having the capable of describing all the non-properties of the compound, then the actual structure is the intermediate or the resonance hybrid of these structures. This phenomena is called as resonance, and these structures which is called as resonating structures, and the intermediate of this structure is called as resonance hybrid. Let us take another example of resonance to explain, that is benzene. Benzene is represented by a cyclic structure, that is 6-carbon cyclic structure having alternate single and double bond. As it is shown here, it have alternate single and double bond. So we expect that here two different bond lengths should be there, because there is a double bond, C double bond is also there, and C single bond is also there. So we expect that we'll be getting two different bond length, because we know that the bond length between the two carbon, that is double bonded, is different value from the bond length between the single carbon, that is between the two carbon. So we expect that we'll be getting two different values, that is two different bond length will be expecting, because it have a double bond also, single bond also. But it is experimentally it was found that all the CC bond, that is both the single bonded carbon and the double bonded carbon, the bond distance is 139 pm. That is, it is experimentally found that benzene has uniform CC bond distance, that is 139 pm. And this value is not the value of a single bond, and it is not the value of double bond. It is an actually intermediate value between the CC single bond and between the CC double bond. So what the value experimentally we got, the carbon-carbon bond length value, that is 139 pm, is an intermediate value, that is intermediate value that is in between CC single bond and CC double bond. So this is what it shows, that the actual structure is the resonance hybrid, that is a intermediate between the two structures. So these two are the resonating structures, and this one is the resonance hybrid. So the actual molecule, its all properties can be explained by the resonance hybrid, but it cannot be fully explained by the different structures made for the benzene. So that is what come up with the concept of resonance. Let us take another example. That is nitromethane. The resonating structures of nitromethane is shown here. So here also you can see the two different possibilities are there. That is the two different structures are possible. So that is actually the position here is different because the double bond position get differ here both the cases. So what is actually happening here? So the actual molecule, its all property can be explained by its resonance hybrid. So, however, it is known that here two NO bonds of nitromethane are of the same length. That is intermediate between NO single bond and NO double bond. As we have already discussed the case of benzene, here also when we expect that here there is a N double bond O and N single bond O. So we expect that the bond length will be different because double bonded bond length and single bonded bond length is different. So we expect that we will be getting two different bond length. But actually when we find experimentally there will be a same bond length. That is what it is explained here. There is a same length. That is actually an intermediate value between the NO single bond and NO double bond. So that is actually what we call as the hybrid structure. So the actual molecule or the actual structure of the nitromethane is therefore the resonance hybrid of the two canonical forms, that is the first and the second. These two are the resonating structures. And what is the other name for this one? That is canonical forms, first and second. So these are the resonating structure and the actual molecule will be the hybrid of these two, are the hybrid of these two. So it is very important concept of resonance because the resonance structures, or which is also called as canonical structures or the contributing structures, these are the hypothetical and individually do not represent any real molecule. So the resonating structures independently or individually it do not represent any molecule, but the resonance of this will explain all the properties of the molecule. So these contribute to the actual structure in the proportion to their stability. So the energy of the actual structure, which one is the actual structure? The resonance hybrid of the molecule, that is the resonance hybrid is the actual structure, and the energy of the actual structure is lower than that of any of the canonical structures. So if two canonical structures, or we can call resonating structures, are there, so what is the hybrid of these? That is having the energy lower than any of the canonical structures. And the difference in the energy between the actual structure and the lowest energy resonance structure is called as resonance stabilization energy. So what is resonance stabilization energy? As we know that for a molecule there will be more than one possible structures are there. That is for some molecules. So these structures are called as resonating structures, and the actual structure is the resonance hybrid, and the energy of the resonance hybrid is always lower than any of the canonical structures. So the difference in the energy between the energy between the actual molecule, that is the resonance hybrid molecule, and any of the resonating structure molecule, that difference in the energy is called as resonance stabilization energy, or simply we can call it as resonance energy. So the resonating structures, the following rules are applied while writing the resonating structures. So what are the rules? The resonance structures have the same position of nuclei. That means when you are making the resonating structure, the position of nucleus will not be changed, and the same number of unpaired electrons. When we count here, they have same, whatever the resonating structures, the unpaired number of electron will be same. The contributing structures, which is called as canonical structure, should have nearly same energies, and all the atoms should have octet of electrons. That means all the atoms should have octet of electron, means should have 8 electrons surrounding to it, except the case of hydrogen, because we have learned that in hydrogen only single shell is there and maximum 2 can be accommodated. So the hydrogen gets satisfied by getting 2 electron. That is, it will not have 8 electron, but other all atoms they will get stable when they get 8 electron. That is what it is called as octet. So all the atoms should have octet of electron except the hydrogen. So resonance effect can be discussed in 2 types, that is positive resonance effect. So better we'll take the example of aniline. These are the resonating structures of aniline. Now when we look at the structure, these are the second structure, third structure, fourth structure. These are the resonating structures. Now when you look at here there is a shifting of electron. That is, when you look at here, there is one lone pair on this nitrogen that gets shifted to this bond. So now it formed double bond here. So when the double bond is formed here, this bond, that is a bond which is here, it will get that electron gets shifted on this. That's why you can see the negative charge on this one. Next, this negative charge forms a double bond here. And when it forms a double bond, this double bond will break and that electron will shift to this position. So what it is clear from this one, here there is a delocalization of pi electron. That means the electrons are shifting to in this ring. So that is what we can find here, the negative values. In some position there is more electron density. Like in the second structure, here you can find that more electron density is on the ortho position. This position is called as ortho. As the negative charges is on the ortho position for the second structure, so we can say that more electron density is at ortho position. But what about the third structure? In the third structure, more electron density, that is, you can see here the negative charge is on the para position. So we can say that greater electron density will be at para position. What about the fourth structure? In the fourth structure, negative charge is on the ortho position. This is also an ortho position. As I told you, if there is any group, if this is any group, the adjacent position, this is called as the ortho position. This is an ortho position. This one will be a para, and this is meta, and this one is meta position. So the adjacent to the group, that is called as ortho position. So in the fourth structure also, the negative charge is on the ortho position. So we can say that greater electron density is on ortho position. So how we make the resonance hybrid of this one? By making a circle. So instead of writing the single and double bond, what we can make a circle there. That is what the resonance hybrid of this one. So why it is called as a plus R effect? That is because the substitute that is the NH2 group here, that is a substitute which has a tendency to donate the electron to the ring. That means we can see here the electrons are shifting from the substitute to the ring. That means the substitute has a tendency to donate the electron to the double bond, or we can say to the conjugated system. The system is called as conjugated system. That is alternate single double bond system is called as conjugate system. So here the substitute, that is actually the NH2 group. The NH2 group is a substitute which has a tendency to donate the electron to the conjugated system. Therefore, this effect is called as it is called as a positive resonance effect, or which is also called as plus R effect. So, what is plus R effect? That is, if a substitute has a tendency to donate electron to the conjugated system. You can see here the electrons are donated to the conjugated system, or we can say to the benzene ring here. So, this effect is called as a positive resonance effect because here the positive charge is developed on the substitute here, and the negative charge because the electrons are transferred from the substitute to the ring. So that's why the positive charge is on the substitute and the negative charge is on the ring. So that is what it is called as plus R effect. So the plus R effect, in this effect, the transfer of electron is away from the atom or the substitute group attached to the conjugate system. So this electron displacement makes a certain position in the molecule of high electron density, as it is shown here. As I already told, in some position there will be greater electron density, that is at ortho position. When you look at the resonating structure on the second position, on the second structure and in the fourth structure, greater electron density is at ortho position, but in the third structure the greater electron density is at para position. So that is what the plus R effect says. Next is the negative resonance effect, which is called as minus R effect. Let us take the example of nitrobenzene. The formula for nitrobenzene is C6H5NO2. Now when you look at the resonating structures which is given here, as I told you, this is the symbol which is representing the resonating structure, that is double-headed arrows. That is the resonating structures which can be separated by these double-headed arrows. In nitrobenzene, you can see that here the shifting of electron takes place from the benzene to the substitute. That means from the conjugated system to the substitute. Which is the substitute here? NO2 group is the substitute here. So here the shifting or the displacement of electron is taking place away from the conjugated system. That is, it is taking place towards the substitute. And because of this one, the positive charge is developed on the ring, that you can see at the ortho position and para position. Here positive charge is developed and the negative charge is developed on the substitute. So that's why it is called as minus R effect. So what is the negative resonance effect or the minus R effect? That is, if a substitute, that is here NO2 is a substitute, has a tendency to withdraw the electrons from the conjugated system, because here the shifting of electron is from the benzene ring to the substitute. That is actually here the substitute has the tendency to withdraw the electrons from a conjugated system towards itself. That is, this effect is called as minus R effect or the negative resonance effect, because as the electrons are withdrawn from the conjugated system towards the substitute. So what is actually developing? The positive charge is developed on the ring and negative charge is developed on the substitute. So negative charge is developed on the substitute. This is called as negative resonance effect. So the effect is observed when the transfer of electron is towards an atom or the substitute group attached to the conjugated system. As a case of example in the nitrobenzene we can see. So these are the two types of resonance effect we have discussed. Now let us see whichever substitutes can form positive resonance effect and which one can show negative resonance effect. So we have to remember this one. The plus R effect is shown by groups like halogen group, OH group, OR, OCOR, NH2 group, NHR, NR2, NHCOR. So these groups, if it is there with a benzene ring, so at that time it show plus R effect and that is positive R effect. And if the groups like COOH group, that is a carboxylic acid group, aldehyde group, ketonic group, nitrile, CnNO2. So when these groups are there at the time with a benzene ring, then it shows a minus R effect. So these two you have to remember in order to write the resonating structures. So we come up with a new term here, that is a conjugated system. What is conjugated system? The presence of alternate single and double bond in an open chain or in the cyclic system is termed as a conjugated system. As in the case of benzene, we can see there is a alternate double single. You can see again double single double single. So this alternate single and double bond that is in the open chain or in the cyclic system, that is termed as, that system is termed as conjugated system. So this is all about this video, which is very important topic. So all of you go through it and write the note of this. So this is all about this video. Have a nice day.